Welcome back, children. We'll continue with the lesson now. In the previous class, we discussed the helical path of a charged particle. The charged particle enters a magnetic field at an angle other than 90 degrees. Then it will follow a helical path. The vertical component of the charge, or the velocity of the charge, will make it go in a circle. And the horizontal component will not be affected by the magnetic field at all. So, the horizontal component, the component which is along the magnetic field, will be unaffected. So, this charge will make a circle and then will also move in the direction of the magnetic field. So then you will have a helical path. So this is what we discussed in the last class. Okay. Actually, you can see the effect of this in real life. The effect of the equation F is equal to QV cross B, okay, which results in a helical path of the charges, the moving charges, can be seen in this world. If you either go to the northernmost parts of the world or the southernmost parts of the world, then you can see the effect of this. The effect of this equation, or one of the effects of this equation, is called as the Aurora Borealis. Aurora Borealis means northern lights. Boreal means north, and then Aurora means light. Boreal means north and Austral means south. So that is the reason why you call the continent down south as Australia. Australia means the southern land. So as I said, you can see this effect either in the northern parts of the world or in the southern parts of the world. When you see the same thing in the southern parts, then you call this as Aurora Australis. This you can see in the Antarctic regions. Okay. Okay, I've given you the names, Aurora Borealis and Aurora Australis. But what do they mean basically? If you go to Canada or Greenland or even the Arctic, any part of the Arctic Circle, then in the nights you will be able to see a tapestry of green and pink lights dancing. It is like a cloth of green and pink light, dancing in the wind. So you can see that it's a long cloth, it's a very high vertical cloth, as if like they're hanging from the heavens, and then they'll be moving. Why does it happen? It happens because of this force. F is equal to QV cross P. What does it mean? What am I even telling you now? The Earth is a giant magnet. You know that. Okay. It is a north pole and also has a south pole. Actually, the north pole is the magnetic south pole and south pole is the magnetic north pole. But let's not get to that yet. So the Earth is a giant magnet. And now you have the Sun. The Sun keeps sending the solar winds. What are solar winds? Solar winds are charged particles. So these charged particles keep traveling in space from the Sun to all different parts of the solar system. So a part of the solar wind also reaches the Earth atmosphere. And solar winds are charged particles. Now the charged particles are moving and they are in the Earth's magnetic field. So clearly a moving charge in the magnetic field will have to follow a helical path in general. If it is perpendicular to the magnetic field, then it will follow a circular path. But if it makes an angle with the magnetic field, which is not 90 degrees, then it will follow a helical path. So then what happens is this. Let me draw that picture. So this is the Earth. And let me look at it not from, not from the side view, but from the top view, but at a slight angle. Let me say that this is my north pole, which means that the south pole is on the other side, which I can't even see because I've just tilted Earth like this and I'm seeing it. So if this is the north pole, the south pole is there. Okay? So the magnetic field lines of the Earth will be like this. Something like that. Something like that. Okay. So this will be said north and south we call, but this is actually south pole. So the field lines, the field will be like this. The Earth's field will be like this. So north pole. A north pole is what you call as north pole, as I said, is a magnetic south pole. We'll get to know about it later. Okay, so the field lines are like this. Okay, because that's not important now. So now the charged particles come. Okay, then let's say they get here. So they make an angle with the magnetic field. The velocity makes an angle. So then what's going to happen now? And it's going to follow a helical path. Likewise, everywhere you're going to follow a helical path. Okay, so the charged particles, so there is a concentration of the charged particles either at the north pole or at the south pole, but at every other place they are distributed. But all of them will go to the north pole because they need to follow this path, right? So they need to move along the line, the magnetic lines, so field lines. So clearly, so then so everything will be coming to the north pole or to the south pole. Okay, depending on what kind of charge you have and stuff. So they come there. As they come there, then you see there is a very high concentration of these charges in the northern parts of the world. Okay, they all come there. So as they come, they collide with the molecules in the atmosphere. They excite those molecules. These molecules are excited and ionized, and then they go and the charges will recombine. They'll do all kinds of stuff basically. Okay, the charges will get excited. Okay, and then again they'll come back to their original ground state. Okay, when they come down, then they'll let out light. So that is what you see. Okay, this part, charge is getting excited, going to a different orbit and then coming back. All that we'll study later. But what happens is, in a nutshell, these charges, the solar charges from the solar wind, they collide with the molecules of the atmosphere, ionize them, excite them, and then as the excitation, the excited molecules come back to the ground state, they let out light. Oxygen will let out green light. Nitrogen will let out the pink light. Now, since oxygen and nitrogen are the major components of the atmosphere, you see this green pinkish light happening there. Why does it not happen anywhere else? It's because there is not enough concentration there. But all of them, all the solar wind, the charges from the solar wind which reaches the earth, okay, all of them will be concentrated either at the south, or either at the north or at the south. So there they will collide with a lot of molecules and produce this light. So you call this as Aurora Borealis, if it happens in the north, northern lights. And you call this as Aurora Australis, if it happens in the south. It's a very interesting phenomenon. Search for it, take these words, search for it, for Aurora Borealis in the internet, then you will get some amazing pictures. They're surreal pictures. I mean, fantastic to look at. Okay? It's like a tapestry hanging from heaven, as he said. And it moves because the molecules in the atmosphere are in motion all the time. So the tapestry also moves. It's fantastic. Search for it in the net and you will love it. Okay, now let us talk about moving charges in a combined electric and magnetic fields. Okay, these moving charges in combined electric and magnetic fields. What we'll see now. Suppose there is a charge which is moving in this direction. Okay? And if I keep both the fields E and B, then what do I know? I know that the resultant force is given by this equation. F is equal to Fe plus Fb. And this is simply Q into E plus this would be Q V cross B. And this is what we call as the Lorentz force. Okay. What if I keep B and E perpendicular to each other? If B is like this, okay, and E will be like this. If this is B and if this is V, then what will happen? It's a question. Let's see. I'll draw this. This is a point in space where the charged particle, preferably positive charged particle, is moving in this direction. This is the velocity, the charged particle. Okay. And let us suppose that there is a magnetic field perpendicular to this charge, this velocity. Let's say it is in this direction. Probably like this. I don't have a proper red pen, but anyway. This is my B. Okay, which is 90 degrees to it. Okay. and I have the electric field 90 degrees to both of them. This is my E. Then what is going to happen to it? So let me do it this way. Let's say this is my V, and this is my E, and this is my B. So this is how it is. Okay. So what will happen now? So V is in this direction, V is in this direction, B is in this direction, and E is in this direction. Then what is going to happen now? Clearly, this is a moving charge. So the moving charge, because of this magnetic field, will experience a force. And which direction will the force be? I've taken this to be a positive charge. So QV cross B will give me the downward direction. But this charge is also an electric charge, and I am keeping it in an electric field. So this will experience a force in the direction of the electric field. So there is also an upward force. Okay. Again. So because of the magnetic field, this will experience a downward force. So V cross B will give me the downward direction. And because this is an electric charge, and because it is kept in the presence of an electric field, this will experience a force due to the electric field. So this charge, as it is moving, it will experience both a downward force and an upward force. So the net will be the result of these two forces. If the downward force is equal to the upward force, then the charge will go unaffected, because this force will be cancelled by that force. If this is greater, then it will make a circle in this direction. Okay, it will start doing it, because this is going to be pulled by the magnetic field. If this is greater, then it will make a circle in this direction. You can see that. Okay. So the net force will be a combination of these two forces. So the net force acting on the body, F. Okay. I'll take it as magnitude. F is going to be equal to Fe minus, okay, I'll put the direction side now. Just put the direction side now. So anyway, if you take the magnitude, then this would be Fe minus Fb, or Fb minus Fe, and then you can choose the direction which way. So you can get the magnitude here, and after that you can get the direction depending on which one is greater. Okay. Anyway, so this let's take this special case where the force due to the electric field is equal to the force due to the magnetic field. In that case, Fe minus Fb will be 0. It will cancel each other, right? Completely. So is equal to Fb. Then what's the magnitude of Fe? It is simply QE. QE is the magnitude of Fe. And what is Fb? That is QV B sin theta. But what did we say? The angle is 90 degrees between the velocity vector and the magnetic field vector. So sin 90 will be 1, so it will just be QVB. So QE is equal to QVB. So Q and Q will cancel. Okay. And this is equal to 0. That's a special case we are taking. So look at this. Now V can be expressed as E by V. So what does it tell you? What does it tell you? I keep a magnetic field in this at this point in space in this direction, and I also keep the electric field in this direction, and I allow charges to move in this combination of fields. Now they are called as crossed fields, by the way. You are calling like crossing B and E, so they are called as crossed fields. B and E are perpendicular to each other. Okay, so in this crossed fields, and you are allowing a charge to move at an angle of 90 degrees to both of them, okay, then what is going to happen? What happens is, if the charge has this velocity which is equal to E by B, then the charge will go unaffected by both the fields. But if the charge has any other velocity than this E by B, then it can either move upwards or downwards. It can make I told you, it will make some kind of a circle there, upwards. If FE is greater than FB, then it will make this kind of circle. If this is greater, FB is greater than FE, then it will make this kind of circle. Okay? It won't go unaffected by both the fields. So this has a profound implication if you look at it. So if I have a collection of charges, they are all moving in a particular direction with different speeds, like sprinters in a race. Okay, all the charges are moving in the same direction, but they all run with different speeds. Then, if I keep these fields, the crossed fields of E and B, and what happens now is that I can select the charges with a particular speed. By adjusting my E and B, I can select the charge with this speed. If I want, say, 10 meters per second or something, all I need to do is adjust my E by B such that it gives me 10 meters per second. So the charges which move with 10 meters per second speed, okay, will go unaffected, so I can collect them. Others will go either down or up. They will leave this axis, leave the straight line. So J.J. Thomson used this method to find the specific charge of an electron, E by M, the ratio, okay, in 1897. And this is still used in mass spectrometers. Okay? Mass spectrometer is used to find the specific charge of ions, okay, with different masses and charges. Okay? Ratio is still used. So this is called as the velocity selector. Right. So crossed fields can be used to select charges of a particular velocity, because charges which do not have this velocity, which is equal to E by B, will drop out. They won't travel straight. They will either go down or go up. And what speed you want can be decided by this quantity E by B. You can adjust E and B in such a way that you get the speed of your choice, and only those particles will collect on it. So you call this as velocity selector. Hope this is clear to you.